isn't what you think it is.
I love guy theory.
Not helpful.
On the contrary, actually. I don't have a pencil.
Oh, can I borrow a pencil? Alright guys, section 2.7 says non-linear inequalities. What do you see in the very first example at the beginning of notes?
Factor it.
Non-linear.
Non-linear.
No. Jaden was right. No. He said quadratic, I said non-linear. Are we both correct? Because a linear wouldn't have a square, would it?
No.
Okay, so quadratic, good. Non-linear. Now, is a quadratic the only type of non-line out there?
No.
Non-line just means anything but a line, true? So maybe a quadratic, maybe a cubic, maybe a quartic. Oh no! Basically all polynomials minus first degree. But that's not all. How about square roots or absolute values or rational functions? The homework that's due today that we're supposed to be grading, which we will after we do notes. Non-linear inequalities. Look at the example, guys. Isn't it an inequality? So a lot of you guys are like, factor, and I don't disagree. Factoring is good and all, but after we factor, how do we solve if it's less than 0, not equal to 0? No. Not equal 0. That'd be easy. It'd be x equals 3 and x equals negative 2. But we're not looking for equals. We're looking for less than.
So it'd be negative 2. Because negative 2 is less.
It's the 0.
But
right?
Less than, that one's less than 0. 3 is not less than.
Well, problem is, don't we need the whole thing to be less than 0? So what happens if you plug in negative 2? Wouldn't that be 0 times anything is equal to 0?
Oh, you
Can't do 3 either, because 0 times anything is 0, which would be equal. So we need the whole product, the multiplication, to be 0. Negative 3?
Well, you don't want it to equal 0, right? You just want it to be less.
Negative 3. Well, we're just like throwing in random x's right now.
Negative
There is a
3 and 2.
strategy. You're right. But if we throw in negative 3 right now, negative 3 minus 3 is negative 6. Negative 3 plus 2 is negative 1. What's a negative times a negative?
Positive.
And a positive is greater than. So wait a minute, hold on. Emily just said negative 3, and negative 3 is a no. What other types of numbers would be no's?
Imaginaries.
Okay, well, yeah, we're not looking for imaginaries. We're looking for real numbers.
Anything positive is going to be done.
Negative 3. Oh, is negative 4 going to be a problem? And negative 5, and negative 6, and negative 7, and negative 8? Aren't they all going to be negatives times negatives? Okay. So that's like a whole range of numbers. A whole interval of numbers. Well, wait a minute. Well, how high can we go? How about negative 2?
No, we can do negative 1. That'll work.
Oh, okay. So negative 2 doesn't work because it's 0, but negative 1 does work because that one would be a negative, but this one would be a positive, right?
Yeah, that's what I'm saying.
And a negative times that. Okay, so how long will that work? How about 10? 10 doesn't work. Okay, so negative 1 works, but 10 doesn't. So there has to be some sort of cutoff on the other side, too. Hey, it kind of sounds like we're talking about a number line, don't you think?
Oh, I have to do that.
I mean, you guys randomly picked negative 3. Emily just kind of, I think she saw that and went the other way. She's pretty good at that. Negative 3. But do you realize that we got up to negative 2 and it wasn't working, and then all of a sudden after that it started working? Did anybody notice that? Negative 2 was a separator between the non-working and the working. Because negative 3 was a no, but negative 1 was a yes. Hey, negative 1.9 would also be a yes. Positive times a negative. Negative 1.9. Everything right directly after negative 2 is fine. Up until, okay, hold on, we just realized 10 doesn't work. So there has to be some upper bound. Wait a minute. Who is negative 2? What made him so special? On one side didn't work, on the other side it did work.
Negative 2 equals 0.
Negative 2 is a 0. So guys, if negative 2 was important and was helpful, what else do you think might be helpful also?
Positive 3.
How about the 3? So what if we break a number line down only using the zeros, and all we have to ask ourselves is, let's check it. Negative 3, negative 4, negative 5, negative 6, all of those were false with our inequality, so they weren't part of our answers. Guys, have you tried 3 yet? Is 3 going to work?
No.
Is 2 going to work? Is 4 going to work? See it? 4 minus 3 is a positive, 4 plus 2 is a positive times a positive fails.
So
Basically,
greater than negative 2.
this is the entire section. It's figuring out what values are our separators, what values break our number line down into intervals of x's, and figuring out where is inequality true, those are our solutions, and where is the inequality false, those are not our solutions. That's the entire section. But we have to figure out which numbers to put in. For quadratics, it will always be the zeros. For polynomials, always the zeros. But we're going to see other functions too when it gets a little messy. Let me write the answer. I see questions. Let me write the answer. So, if I were to solve, my answer is all the x values in between negative 2 and 3. Another way of saying that is all x's greater than negative 2 and less than 3. Why is the interval open? Why am I not allowed to say or equal to? Why do the zeros not get included?
Because it's somewhere.
It's less than and not or equal to. Jade.
Oh, yeah,
I answered it?
Yeah.
Ah, go team Sophia. Oh, I thought you had a question. Okay. Never mind. That's up.
I'm so confused on writing it out. Like, I understand the logic of it, but actually writing it out, like.
Oh, I just realized all the numbers in between, which with inequalities, I can put x in between by saying you're higher than, you're to the right of that one, and to the left of that one.
And what about the thing above it?
Oh, this is just true. Oh, this is the snazzy interval notation. Remember where we had how left to how right for
Okay.
like increasing, decreasing domains and ranges. It's terrible.
So it would be like how left you can go to negative 2, how right you can go to 3.
Got it. And the comma is basically everything through. So it's not a point, it's a beginning and an end.
Okay.
And remember sometimes we had brackets,
Yeah.
but not this time because neither one was allowed to be included.
Okay.
Now guys, if we were doing a number line, wouldn't we technically put a hole and then a hole? Like if we were doing an old fashioned, it'd be above. Sorry, I just didn't have one. We would say from here to here, but I'm not allowed to fill the circle because it's not allowed to be included. That's old school number line bracket.
So the only way you figure this out is through
Testing intervals.
tests.
But you don't know what intervals to test until you figure out what numbers to put as your separators. So, check it. What does page say? Polynomial inequalities. Key numbers, all the zeros. Oh yeah, they were the key guys. Weren't they the key ones we had to put in? Key as in most important, as in main, as in, well, in calculus we call them critical numbers. You don't know what a derivative is, so I can't use that term yet. Key numbers, the main ones, the important ones. And if it helps, the key numbers are going to be the same thing as my number line separators. My number line separators. Separate. Why can't I spell separate? Separate. So, for polynomials, there it is. Please put it on my desk. Thank you. Glad to read it. For there we go. Polynomials, all the zeros. Those are going to be my separators. For polynomials, all the zeros. A polynomial can only change signs at its zero. So check it. I use my 0 of negative 2 in my number line. I use my 0 of 3 in my number line. And all I had to do was check each interval for true or false. And I only had to technically plug in 1 point in each one. What's something to the left of negative 2? Negative 3 is false. Great, they're all false. All I had to do was check 1 in between. 0's in between. It's true. Yay, they're all true. All for 1 and 1 for all. 1 above 3. 4 was false. They're all false. Now, check it. Hold on. What's the other category of function, just according to this page, that you know you're going to see? Polynomials, yes. Find the zeros, make number lines, and check and test. But what's the other side? Who comes next? Okay, somebody said nothing, and someone else actually read what was there. Rational. Polynomial key numbers that we're going to use as separators in the number line are the zeros. Rational key numbers are going to be the zeros or the undefined points. Zeros or the undefined points. Okay, rational. Remind me, guys, in section 2.6, what were you seeing in that entire homework? Functions that had... Oh, okay, there were asymptotes. There were horizontal ones where you had to check the degrees of top and bottom. There were vertical ones where you had to look in the bottom. Wait, I'm saying bottom. Why am I saying bottom for rational functions? Aren't they tops and bottoms? Aren't they f of x's over g of x's? Aren't they numerators and denominators? Right? Does that make sense? I'm saying bottoms because section 2.6 had functions and denominators. There was always an over x plus 2 or an over x squared minus 4 or an over. There was a top and a bottom. So polynomials, whatever, they're f of x's. What do? We set them equal to 0 and we solve with factoring. Rational key numbers. We need to find the zeros, which will be still just like this, but who's f in context of my rational number? Numerator or denominator? So when I see zeros, well, zeros, I could think numerator equal to 0. Undefined points, well, undefined points, it sounds like problem points. Problem points sound like discontinuities. Discontinuities sound like domain problems. Where do domain problems, maybe asymptotes, maybe holes, where do they show up? In the numerator or the denominator?
The denominator.
Got it. So check it. For polynomials, we're doing zeros of the polynomial, and for rationals, we're doing zeros of the numerator and denominator. There you go. There you go. So the shortcut for key numbers for a rational function is if you have some dude called, I don't know, p of x, just because that's his name. We'll do r of x for rational. How about that? If r of x equals an f over g, I like thinking about key numbers with a little pitchfork, because the pitchfork says set the top equal to 0. If you have an r of x, if you have a rational function with a numerator and denominator, for key numbers, the little shortcut I think about is set his top equal to 0 and set his bottom equal to 0. I know it's silly, but it's something that we use in calculus a lot. We have numerators and denominators. We've got to get them all nice and pretty and simplified so we can set the one numerator equal to 0 and the one denominator equal to 0. But what was the point of this entire page? To do the inequalities, we have to set up a number line with these separators. And the separators we call key numbers. For polynomials, zeros. For rational, zeros at the top and the bottom. And that's it. Then we've got to test it. So maybe the idea is not too crazy. Let's see where. Okay, class. Let's do another example first. Then we'll come to steps. Oh, we already did this one. That's okay. I'll show you the snazzy way of doing it. Okay. So the snazzy way of doing it. You can put your pencil down if you want. We already solved it. Key numbers. The snazzy way to do it would be, and let me even show you the page of steps. Maybe you want to write down the notes, and maybe you want to see if you understand them first. Here are the steps to solving. Find all key numbers. Well, for this, it's a polynomial, true? So I'm looking for just my zeros. And my zeros, I set my polynomial in its factored form. If you can do fast, or maybe take a little bit longer. Okay, so for key numbers, I'm finding my zeros. Yes, x equals -2 and +3. Those are my zeros. But after I find the key numbers, I need to use them to mark intervals. After I find my key numbers, I'm going to use them to mark intervals on a sign chart. Well, on a sign chart, if you want to think, you can think number line. But technically what you're doing is you're splitting the domain of the original function, negative infinity to infinity. You're splitting it up with those key numbers, and you're making intervals. Now, it depends on the inequality as to whether these are going to be open or whether they're going to be closed. The nice thing is the infinities are always open. The nice thing is the infinities are always open. But in sign charts, we have to check the inequality. We close if we have less than or equal to or greater than or equal to. And we keep it open if we have a less than, a greater than, or not equal to. We close it if we have an or equal to, and we open it if we don't. So in this one right away, I could see just by looking at my inequality and thinking about open intervals only. But once I've thought of, okay, what's left of -2? What's in between -2 and 3? What's to the right of 3? And Jaden, just intervals, right? How left, how right? And then how left, how right? And then how left, how right? Then I just have to think about, okay, so these are my intervals if I'm labeling. I need to pick a test point. And I need to think of true or false. So what's some sort of test point that we picked on the left of -2 or inside this interval?
-3.
Yeah, like -3 or -4. So we have to go, remember, if it helps, 0. I'll put a little dash because it's not included down here, but 0 is in between. So getting farther away from 0 would be like a -3. Oh, 0 itself could have been that one, right? And then somebody that way could have been, sure. And when we plugged in, we saw that this ended up, now sometimes this gets a little nasty as far as plugging in. This could take a little bit of work. So some people might add like an extra row to our chart. And they might be like, you know what, I can't do all that mental math. Like, that's not a good idea. I should probably show a little bit of work. So you could theoretically show some work. And here's my hint for showing work. So we actually plug in, and then we figure out true or false. If I were you, if you already factored the original inequality, maybe you should think about this form instead of the other form when trying to figure out less than 0. Maybe you should figure out or use this form instead of the other one. Because the other one, you have to plug into like a squared minus an x and then minus a 6. This one, I can just say, what's -3 minus 3? -6. What's -3 plus 2? -1. Oh, hey, that's a positive, not negative. Oh, false. Plugging in 0. 0 minus 3. That's -3. It's just a little easier in your head. 0 plus 2, positive 2. And negative times that. Well, it's a negative. That's true. Negatives are less than 0. And then 4, once again, we figured out 4 minus 3 is 1. 4 plus 2 is 6. Which is not less than 0. That's greater than. It's another false. We got to our final answer of this inequality is true when x is within or in between. So we already found that answer. This is just the technical procedure that these steps are talking about. Find all your key numbers. Polynomial, look for zeros. Rational, look for zeros up top and bottom. Mark intervals from that. From that number line, we can make a chart. From that chart, we can technically just test one here, one there, one here. True or false? The true column, that interval is a part of my solution. Jade, go.
Do we have to do this chart?
Well,
like,
it's up to you, but you
like
have
the
to
first
go
time
through
you
the.
solved it, like you just used the number line.
But you have to go through the procedure. So do you have to use the chart? Technically, no. But you do have to follow the procedure to be able to get the right answer.
So if you go through like, okay, there's nothing that can be left and
The logic in the number
right.
line
That's fine.
does the same thing, as long as you fully understand. Does that make sense?
Yeah.
The logic in the number line As long as you're thinking of, I'm taking one, I'm plugging in, I'm testing true or false. I'm taking one, I'm plugging in, I'm testing true or false. You can technically do this in the quick number line version like I did before. Just be careful. Now, when I say compare signs, don't I need to check positive or negative, right? But that only works. Only signs when I'm dealing with less than 0 or greater than 0. Because less than 0 is another way of saying negative, right? Does that make sense, right? Greater than 0 is another way of saying positive. So when I say compare the signs, I'm specifically talking about what if 0 is on one side, and, well, you could even do or equal to, but less than 0, we're talking about negative numbers. Greater than 0, we're talking about positive numbers. If you don't have a 0, you can't just look at the sign. You're going to have to look at the whole thing. But right now, it was enough for me to say positive, fail, negative, check, positive, fail. But that's only because it was a less than 0. So it's saying, give me the negatives, please. And I'm like, sure, I'll find them for you. Right there, in between -2 and 3. So comparing the signs, that technically is only if we get a 0 on one side. If not, then we can still do this whole entire process, but you're not just looking at the signs, you'd be looking at the numbers too. Boop. Okay. So, where does this leave us? Or where does this take us? I'm going to go ahead, and if you guys don't mind, let me move this snazzy way of doing this example. Let me move it up one slide so you can still see the steps as we go peek at. What? What is this? Why am I going to also move this up and say, oh no, you don't belong with the steps. Hold on, you're not a new problem. Why does this show the exact same thing that this shows?
It just was not touching.
If it's a graph, I mean, we did this graph a second ago. Number line of the x's in between -2 and 3. Those were the true x's. What's that graph from? Where it, what do you mean by it? You're right, but which one? The graph of what? If you think about this guy as a function, guys, isn't he a parabola? And isn't he a parabola with zeros that's been shifted down? Check it. This is who the function actually is. So why does -2 to 3, but not including work? Where is the parabola for all of these places? Isn't it below 0? Do you see it? So technically, if you're trying to answer that, and if you know a graph, you can just look at it and say, oh, hey, when are you below the axis? Oh, yeah, you're below the axis here to here. Oh, sweet. See, I feel like, well, forget that whole process. Why don't I just graph every single one and see when it's below? Well, below only works if you're less than 0. What if I change that to greater than 0? Where would you be looking? Everywhere else, you'd be looking above, right? So if I was to change this problem, not less than, but greater than, then I'd be looking up instead. And that would be different intervals, because that would be looking at, well, I guess for those ones, you'd be thinking of the other guys, which would be the -infinity to the -2, and then the 3 to infinity. It depends on what they ask you as to what you answer. But for below, we were good. -2 to 3. It's just a double check. It's like, oh, yeah, we're all right. So this means on a graph of the function below the axis and above the axis. Okay, sorry. Let's go back to another actual. Ooh, yeah. Yep. Rational function. Which way do I show this? You guys are honors. Can I go straight to the shortcut? You sure? Do you see how this is not a 0? It's a 3. That poses a little bit of difficulty for us. Doesn't make it impossible, just poses a little bit of difficulty. Because as soon as there's not a 0, I'm not just taking this as is and saying, yay, pitchfork, I'm going to set u equal to 0, and I'm going to set u equal to 0. Wait a minute. But it's not 0, it's 3. Oh, I'm going to set u equal to 3, and I'm going to set u equal to 3. Do I want them to be 3 over 3? Or 3 over I don't care what? No, no, no. This will only happen. Oh, stink. That could be 9 over 3, or that could be 18 over 6, or that could, oh, wow. So, pause. If the idea of my key numbers are solutions, zeros are solutions, and undefined points. Hold on, maybe we should separate because we have to find both. For rational, we're looking for zeros and undefined. We're looking for solutions and undefined. Can you guys tell just by looking where this guy is undefined? That's usually the easiest one to pick out. Where is he undefined? 5. Bottom can't be 0. Okay, well that stays the same. That's a key number. But the solutions one, I can't just say equals 0 because he's not 0. How could you solve for the solutions of this if it was an equation? Why not just multiply? Does that make sense? If it's not a 0, I can't quite just do my little pitchfork of, just zeros and then D and E's done. But I can just use my algebra skills and be like, okay, fine, it's not 0, but I'm going to figure out what does answer this problem. What is a solution? AKA solve the equation. So I have 2x minus 7 equals 3x minus 15. You guys okay with the algebra? Doesn't this lead us to 3x minus 2x is 1x, negative 7 plus 15 is 8. I get x, double check me, I think equals 8. Because that'd be a positive x and a positive 8. Okay, so if there's not a 0, okay, it's a little bit nastier. I don't just set the top equal to 0. I have to actually solve it for the solution. There's a little extra step if it's not 0. But do I still have my 2 little numbers? What do you guys like better, the number line or the chart?
The number line.
Chart.
Go with the chart?
No, number line.
My number line should match your chart. I'll see if it works.
Isn't it x can't be 5? Like
right. My undefined is at. My problem is at 5. But you're right, my domain technically for this, which is how I know where the problem is at, is x cannot equal 5. You're right. But why should we probably put a not equal to? What's my inequality? Yay, I'm allowed to close my intervals! But where am I not going to be allowed to close because it's not allowed to happen? So that's a good idea. I'm still going to use the 5, but I have to make sure not to close an interval. All right, you guys who love the number line, because you don't have to write the big old table, I'm going to go ahead and put my 5 and put my 8. And I'm going to put my 5 just to be like, oh, that's right, not equal to. I'm going to put him in parentheses. I'm trying to figure out true or false. I'm trying to figure out true or false. And to figure out my true or false, well, my number line people, I love you. But I'm going to show the table so everyone knows what's going on in the number line. But I'm going to do it quick. My intervals are from negative infinity to 5, open because I'm not allowed to be at 5. From 5 to 8, closed, because I am allowed to be at the solution, just not a D and E point. And then 8 to infinity. I'm going to pick a number. Somewhere on the left, 0 looks easy. He's less than 5. 6 looks so well. It's something in between 5 and 8. And then 9 is something bigger than 8. I'm going to plug in and figure out true or false. And plugging in, well, where am I plugging it into? Original function. And the original function? I just have to ask myself true or false? Technically, you can just go for it as it is and be like, okay, I'm plugging in 0. Negative 7 over negative 5. Is that less than or equal to 3? No, you're right though, because it's a positive 1 2/5. Right? Yeah, it's a positive 1 2/5. That's less than 3. That's good. 6. 12 minus 7 is 5. 6 minus 1 is, 6 minus 5 is 1. Is 5 less than or equal to 3? Okay, that's a false. And then 9 would be 18 minus 7 is 11. All over 9 minus 5 is 4. Is 2 3/4 less than or equal to 3? Yes. So what does that mean? If you guys plugged in, this one should have been true, that one should have been false, this one should have been true. Either one leads us to our final answer of, well, 2 different intervals. Don't we have both negative infinity up to 5, which is not allowed to be included, and then picking up at 8, which is allowed to be included? He's not a DNE, he's an answer. Okay. With this, technically you guys are able to tackle homework. We haven't talked, no, we did talk about graphs. There's one like businessy thingamabob we didn't look at, having to do with profit, revenue, and cost. It's not a big deal. It's not even on a test or anything crazy like that. There is like one domainish question. So there might be a couple weirdish application-y ones at the end that you can't totally do. But you're able to do the process of what we're actually solving for when we do inequality as far as p numbers in number lines or charts. True or false? Let's have you tackle 2.7. I will give grace on the last few problems, and I'll go write a note right now that you both remember. If you skip the last couple application-y ones, I don't mind. So we'll go over homework questions at 2.6 and 2.7 tomorrow. Sound good? Okay. Corrections due by the end of the day. Tomorrow is a big old grand work day. We're going to try to use it to the best of our ability, okay? The better we use it, the better prepared you guys are.